Hello people, welcome to this video. Today I'd like to present something that has really been disturbing me for a long time, and I've been struggling to solve it. Solution to nonlinear overdetermined systems. So if you were to like, what is an overdetermined system? Well, an overdetermined system is a system where you have more equations than unknowns. So I give an example for like for the location of our phones. If you check your phone right now, if you turn on your location, it will show you that there's some radius, but with an error of maybe 30 meters, 20, 50, depending on the accuracy of your phone. But the principle is that your XYZ position, like XYZ position, is unknown, and also the time, because your phone sends signal to the satellites and received by at least 4 satellites. So the time your phone sends the signal is also unknown, because the accuracy of the timing of the satellites and your phone is different, and the synchronization, your phone's accuracy is very different from the accuracy of the satellite. So that brings a lot of error. So for this case, then your XYZ and time the signal is sent to the satellites are unknown. So we have 4 unknowns. So for this reason, if you just want to locate your position roughly, then 4 satellites are enough. So 4 satellites will give you 4 equations, and then we can locate you. But for better accuracy, so if you remember, I said that it will show some accuracy like 30 meters, like 50. But if you want to improve the accuracy or the precision, maybe to within 2 meters, something like this, we need more satellites. So for more satellites, maybe above like 5 or something. But this causes, because we only have 4 unknowns, try to show you here. So these are the 4 unknowns. But if, for example, we have five satellites, will give me 5 equations. So there is one extra equation that we need to solve. Now, this can only also 5 equations can also only give you so much accuracy. But if you want to improve it further, maybe you have 10 satellites, so we'll give you 10 equations, but we only have 4 unknowns. So this is the issue. So this is what an overdetermined system. The meaning of an overdetermined system. So I'll introduce a little bit the solution strategy. Solution strategies for overdetermined systems. To just bring clarity, if it were a linear problem, then what would we do, or what is the physical meaning? Mathematically speaking, actually, that if we have an overdetermined system, that means more equations than the unknowns, then it means there is either no solution or infinitely many solutions. And if we are to present it graphically speaking, because they are like a line in space, a line like this in space, and the axes are many, but in reality we only have like 3D. So this is the X, probably the Z, okay, maybe X, Y, and Z. And because we have run out of axes, so just assume another axis there, and there are many, up to maybe as many as you can imagine. So if we have a line there, so more equations than unknowns either means infinitely many solutions or no solution at all. So the best we can do is to estimate give the best approximation, and the best approximation for a linear case is the projection on the horizontal. So the aim is to reduce this theta, to make the theta as small as possible, and hopefully the resultant solution is good enough. So for linear situations, we have like what we call QR substitution. and then we have solution by normal approximation, and this is where we have a normal approximation, approximation, sorry, solution by normal approximation. Okay, let me normal approximation, and then we can also have so this is where now you need the knowledge of the eigenvalues. There is a relationship, of course, we know vectorially, between a vector and the normal. So the idea of eigenvalues comes in here, but this is much simpler than we need to solve now. So for a linear problem, I think you can refer to mathematical principles or books. Is quite clear. QR on solution by normal approximation. The idea of eigenvalues is quite straightforward. Now, when we are talking about nonlinear systems, it's a bit more complex, and we cannot present in a simple graphical form like we've done before. So the idea here is we need what you call optimization. So there's local optimization and global optimization. For you to understand this, I'll explain in the next slide. So for example, if you have a polynomial like this, so polynomial, and then we know a polynomial has many minima. Allow me to write it in a short form like that. So if you were to look for the minimum of this, you probably start from here, and then you come and probably might get stuck here. So let's call this minimum 1, and maybe 2 and 3. So for this, maybe this is just a local minimum. But if you are interested in the global minimum, as you know, polynomial may have many minima, so then you should have an algorithm that is able to maybe start from here, find a minima there and say that's fine, and then start from somewhere else, say here, come here, find this minimum, and maybe start from there, come and find another minimum, and compare the 3 minima, for example, and find the most or the least, the appropriate, what you can maybe call a global minimum. So this is the point. So this is the issue. So because there is a possibility of having many minima, we need what is called a global search that will give you the most appropriate solution to your problem. And so this is the issue of optimization. And so in Matlab, there are so many options for global optimization. There's multi-strat, there's pattern search, there's genetic algorithm, there's particle swarm, there's surrogate function, simulated annealing. Some are fast, some are slow, some are suitable for certain situations. So you can refer to any Matlab website or online. There's very good community, quite active, will be able to help you understand about the algorithm, about the coding. But eventually you will be the one to decide which of these algorithms is suitable to solve your problem. So that's it. So specifically to my issue I have sensors in a material like this, as shown, this material here. This is a 3D material, and I have many sensors. So say maybe sensor 1, this is sensor 1, 1, 2, 3, 4, 5, okay, and so on. So 5, 6, 7, 8, and so on. So I need, this is an experiment where signals are coming from somewhere unknown. So assume they are coming from here, and these signals are received by these sensors. So all the information we know, just like the idea of the satellite, the phone sends a signal to the satellite. So these sensors are like the satellites. So when a crack happens here, the signals are received by sensors 1, 2, 3, 4, 5, 6, 7, 8. So that's the only information we know. The time the signal is received, that's all. Oh no, sorry. We also know the position of the sensors. This position we can determine, but the position of the crack and the time that the crack occurred, we don't know. So, but to improve the accuracy, we need more sensors than, because there are only 4 unknowns. But if you use only 4, there is likelihood that there will be so much error in the final solution. So to improve the accuracy, we normally choose or elect to use more sensors than the unknowns. So in this case, we'll have 8 equations and 4 unknowns, as I've said before. So the primary, this is just if you look at the principle here, is just the distance. So this is how to get the distance from the sensor to the signal, and is the same as the velocity of the signal. In this case, this is a sound wave, but sound wave traveling through continuous medium. So we know sound wave in air or in vacuum travels at about 340 meters per second, but this is not air, so this is maybe concrete. Concrete is maybe about 3,500 to 4,500 meters per second. So once we know the speed, and this is the time, this time is noted by the sensor, but this is the time of occurrence of the crack, but we don't know it. So 4 unknowns and 8 equations in this case. And of course, because their methods are limited, so there's some this is called residual error or statistical error. There will always be some accuracy issues, so we expect this. So, but this is the general equation. And so to focus specifically to solving our problem, so this is the general form of the equation, but you must conform it to a form that is able to be solved by the software or understood by the software, in this case Matlab. So in Matlab, we have to make this the subject of the equation and then minimize it. But the question is, okay, here you might also have your own ideas, because this is maybe one way to solve. You can also, after you understood, you may also have your own ideas of how to solve. So can you minimize this alone? From what I'm thinking, perhaps not, because if you minimize this, it will give you a very negative value. If it gives you like negative 10 million, it's still minimum, right? So that means this value solved here will not be realistic. So the only way to solve this issue is to square this. If we square, so this is okay, we square, then the minimum must be a value close to 0, is approximately 0. But if you just square this, the minimum maybe not equal to 0, maybe very negative. So to make sure the minimum is close to 0, we square the solution. So just to explain the solution a little bit, after this I will show you the software itself, how it runs. The solution, if you check, these solutions have values. Okay, this was actually a result from a shear test, and this is the principle of shear test. The shear test is we have a sample like this, and we have a load there. Sorry, we have a normal load like that, P, and another normal load like this, and then we shear that plate moves like this, sorry, and then we shear there. Of course there's a plate there, so normally we expect a shear zone here, a shear zone there. So this is where you expect. So the solutions to your problem should be, if this is your sample, if this one was your sample, you expect the solutions to be roughly at the center. Now if you check, so assume this is the, assume the axis is at the center there, so this is okay, let's take the xy only, because so x and y at the center, so that's your 0 0 0. If you check these values, you can see they're very, very small, very small, that will plot somewhere there. So the green are the supposed plot of this, roughly. So this tells you that this is a good way to solve, because from the experience, or from what we know, that the solution is always around the center. So this is a good way to know that this is now good, because the solutions agree with what we know in theory. But not so fast, because I need to go into the software to show you how the code runs. Yeah, so just to demonstrate, we Yeah, so just to explain something a little bit, someone might wonder because the solution for time some indicate negative, but it's just referential time because the time the sensor receives the signal, so we've seen some of those times are negative. So it's possible that because if the time a sensor received the signal is negative, then it means the time the signal originated from its source must be less than the time it is sensed by the sensor. So this is one reason. It's just because of the reference. That's the reason why some of the time indicates as negative, because we are using differential time, and when you find differences, sometimes the differences depend on the reference from which we're referring. So this is how we get some negative values. Yeah, so don't be surprised. But again, like I've said, those values, some of them are within just very few milliseconds, and you can see they are solved very well by the software. Okay, goodbye, and thank you very much for watching.